Hello students, today we are going to learn about equilibrium constant from Nernst equation. Yesterday or in the previous class we have seen Nernst equation. Now we will see its relation with equilibrium constant. For this we have to once again use that equation of reaction half cell that was between copper and zinc. Let's use it again, which we were using in Nernst. So in that reaction we had zinc in solid form reacting with copper in aqueous medium to give zinc in aqueous medium and deposition of copper in solid form. This was the equation and we are using this equation. Now we have to find equilibrium constant. When this equation is undergoing during Daniell cell, the concentration of zinc ions will keep on increasing because zinc metal is being used again and again, and because of this its concentration will decrease. Though we should not use concentration term for solids, the concentration of zinc ions we can say will increase and the concentration of copper ion will decrease. But a time will come when there will be an equilibrium. The rate of forward reaction will be equal to the rate of backward reaction. In that case, let's find out the value. For this, we need the equation P of the cell. EMF of the cell will be equal to EMF of the cell, again that is standard and cell, and then we will be using 2.303 RT by 2F, and we all know this equation, and then we have log Zn 2 plus and C 2 plus, like this, concentration terms. Now if reaction is proceeding, it has attained equilibrium. In that case, the EMF of the overall EMF of the cell of the potential difference will come to 0. It will become 0 as the value has attained stability. So in that case, this equation will be modified. Moreover, in that case, EMF of the cell will become 0. Okay, if it becomes 0, then what happens? We all know the value of EMF of this cell at the beginning. It is 1.1 volt. When half cells are built between copper and zinc, the potential difference of the cell is 1.1 volt. But when equilibrium is attained, this value becomes how much? 0. So the equation can be rewritten accordingly. Then if the overall value has become 0, so instead of these values we are going to put those values once again, so that we can have these values. This overall potential is 0 and this is going to be 1.1. This is what it used to be when a cell is built up between these values, and this equation becomes like this. So this is what is going to happen in that case, and if temperature is 298 Kelvin, these are constants, and again we can take some modifications. this value can be taken to the other side, and in doing so its value will change. It is now negative, it will become positive. So the new value is going to be what? We can write 1.1 is equal to, this is the potential it was giving, and now the equation is 2.303 RT by 2F, and instead of this value, the equilibrium has been attained, so the backward and forward reactions are equal. In that case, we will be using equilibrium constant Kc. So at the place of this whole concentration term, we will be using log Kc. This will be the equation. Now we will find the value of log Kc, and now let's just move these values so that we have log Kc at one side of the equation. So this is going to become log Kc is equal to 1.1 into 2 into, and then we have f, value f. The whole constant can be turned out to be 0.059. We have already seen that this value, the value of R is known to us, temperature. Now we are taking 298 Kelvin, 96500 can be placed here. So the overall value is 0.059, which can be placed over here. So this equation is going to become divided by 0.059. So, and then we have, do we have anything? No, we don't. And then we have to calculate this value. This is going to become log Kc is equal to 2.2 divided by 0.059. So this if this is calculated, this is going to be log Kc will be equal to 37.2881. Now we have to take anti-logarithm. In that case, Kc, value of Kc will be, we will take a look at log table, the value of 0.28, and students, let's find out how to find the anti-log of a given value, because we'll be frequently coming across such questions or numericals in which we have to convert the value into anti-log. So let's see how we are going to convert those values. We have, for example, this conversion in which equilibrium constant is there along with log value. We have to find the log of this value. The log is on the other side of the sign, equal sign. So let's find the mathematical value of this given value, log Kc, and then it will be equal to, the whole calculation comes out to be 37.2881. Now we have these values. Now what we are supposed to do is now find the anti-log of this value. For this, the value left to the decimal will be taken as power. So for example, let's find the value for this 0.2881. Now we have to look for anti-log table in which there will be value for 0.2881. For this we are going to use our textbook. We will turn around to the table given at the back of the textbook, somewhere around here. Yes, anti-logarithms. We have this value. We will look for 0.28. 0.28 is here. This is 0.28, and then we will move to value 8. Value 8 is given in front of this, comes to be 1 point. Though point or decimal is not shown, you have to take it on your own. That means it is 1.941, and then the mean difference, I have taken 1. There is no such value. 0 is given here, so no need to add, and this comes out to be anti-lock value, 1.941 into 10 raised to the power 37. This will be the value which is going for equilibrium constant after the conversion of log into anti-log. 12.28 and 8.1, and those values will be used here, and in that case this is going to be the power of 10. So that value comes around to be 1.94, and 10 is to the power 37 will be the value of Kc, equilibrium constant, when we are considering a reaction going on in linear cell when the electrodes are having these two metals, zinc and copper. Now let's see electrochemical cell and Gibbs energy of the reaction. What is the relation between these two? As you know, electrical work done in 1 second is equal to electrical potential multiplied by total charge passed. So this statement has to be first converted into equation. Let's see what is this statement. It says delta G gives free energy should be equal to minus NF. Now we have gives free energy, number of electrons, and the Faraday constant, and then electric potential. Now the statement says electrical work done. This is representing electrical work done is equal to the product of these two values. This is the charge and this is the electrical potential. These two values together will form or gives energy of the reaction. Now certain things has to be recalled. The first one is, for a spontaneous reaction to occur, delta G should be negative. So if this equation is to be carried out properly, then the delta G should always be negative. But during equilibrium, what happens? The value of E becomes 0. In that case, when equilibrium has been attained, the overall value will be equal to 0. The delta G will be equal to 0. And in that case, no work done will occur. The work done will be 0. So, in order to keep the reaction going, we have to do continuous work. If we want to obtain maximum work from a galvanic cell, then charge has to be passed reversibly. So what happens if we are passing the charge in opposite direction? In that case, the overall result will be negative and the reaction will keep on going. So it has to be kept clearly in your mind. So this is the equation for the electrochemical cell, and gives energy. If this equation needs to be modified for an reaction, in that case equilibrium constant is to be included in the equation. In that case, this will be written as this equation. We have these constants and a variable. In that case, this will be represented in such a manner. But the only thing you have to keep in your mind is delta G should be negative, and we have these values which should be kept in mind.